Dear children, welcome to the 10th module of our chapter Magnetic Effects of Electric Current. In our last module, we already discussed about electromagnetic induction and the first method to demonstrate this phenomenon, that is by using a magnet. Today, we are going to discuss the second activity to demonstrate this phenomenon, that is by using a current carrying coil. So let's start our topic. Let's revise what is meant by electromagnetic induction. Electromagnetic induction is the production of induced current in a coil whenever the magnetic field linked with the coil changes. And last class we have seen the movement of the magnet or the movement of the coil changes the magnetic field linked with the coil so that a current is induced in the coil due to that motion. Children, now we will discuss the activity to demonstrate electromagnetic induction. The last class we already discussed about the first method, that is by using a magnet, and today we are going to discuss about the second method, that is by using a current carrying coil. Look at the picture given here. We have two different coils of copper wire having large number of turns which are wound over an insulating cylindrical roll. Connect one of the coil, that is our first coil, which we call it as the primary coil, to a battery through a key. The key is using to switch on and off the circuit. Connect the second coil, that is coil 2, that we call it as secondary coil, to a galvanometer. See, we have two coils, coil 1 and coil 2 in the picture. Coil 1 is known as primary coil and coil 2 is known as secondary coil. And coil 1 is connected to the battery through the key and coil 2 is connected to a galvanometer which is using to detect the presence of current in the circuit. Children, you already learned in our first module that whenever electric current flows through a conductor, a magnetic field is producing around it, and this is known as magnetic effect of electric current. Here, before you switch on the circuit or before you close the key, there will not be any current flowing through the primary coil as it is connected to the battery. So there won't be any field producing around it. Therefore, no magnetic field linked with the secondary coil. But when you switch on the circuit or when you close the key, the current starts flowing through the primary coil so that a magnetic field will be producing around it. Therefore, a magnetic field is linked with the secondary coil. So, due to this change, that is, before you switch on the circuit, there won't be any magnetic field linked with the secondary coil. But when you switch on the circuit, a magnetic field is linked with the secondary coil. So, a change is happening there in the case of magnetic field linked with the secondary coil. So, due to this change, a current is producing there, that is in the secondary coil, so that the galvanometer shows a deflection. That is, it will deflect to one side. But when the circuit is on, a steady current starts flowing through the primary coil so that a magnetic field will be producing around it, and this magnetic field is linked with the secondary coil also. But there won't be no change in the magnetic field linked with the secondary coil. Therefore, no deflection will be showing in the galvanometer because there is no induced current produced in the secondary coil during this time. Before you switch off the circuit or when the circuit is on, there is a current in the primary coil and thus there is a magnetic field linked with the secondary coil. But there is no change happens in the magnetic field linked with the secondary coil. Children, when you switch off the circuit, there will not be any current flowing through the primary coil. So, there won't be any magnetic field produced around it, and there is no magnetic field linked with the secondary coil. Due to this change in the magnetic field linked with the secondary coil, a current will be produced in it. That means when you switch on the circuit and when you switch off the circuit, a change is happening in the magnetic field linked with the secondary coil, so that a current will be induced in it. Therefore, the galvanometer shows deflection in the opposite direction when you switch off the circuit. So, when you switch on the circuit, it will show a deflection towards one side, and it will deflect in the opposite direction when you switch off the circuit. The induced current is maximum when the direction of motion of the coil is at right angles to the magnetic field, because last module we discussed about the motion of the magnet and the motion of the coil and how it will be inducing a current in the coil. So here, when the coil direction, in which direction the coil is moving and the direction of the magnetic field, if these two are right angles or perpendicular to each other, then the amount of induced current will be maximum. Now we will see Fleming's right hand rule, which is used to find the direction of induced current. See, we already discussed about Fleming's left hand rule, which is using to find the direction of force experienced by a current carrying conductor in an external magnetic field. So this rule we are using to find the direction of induced current. Fleming's right hand rule states that stretch the forefinger, the central finger and the thumb of your right hand mutually perpendicular to each other. Then the forefinger points along the direction of magnetic field, the thumb points along the direction of motion of the conductor, and then the central finger gives the direction of induced current. So I hope it is clear. You can watch the next part to make it more clear.
Let us study electromagnetic induction with the help of a current carrying coil. We have taken two coils of copper wire with large number of turns wounded on a non-conducting roll. One of the coils with the largest number of turns is called the primary coil, which is connected to a power supply. And the other coil is only connected to a galvanometer called secondary coil. Insert the plug key and observe galvanometer for deflection. There is a momentary current in the secondary coil. We can see that the galvanometer deflects momentarily. Galvanometer needle jumps to one side and quickly returns to zero. Disconnect the plug key and observe. We can see that the needle of galvanometer deflected again momentarily, but to the opposite side. As we change the supply voltage, there is a momentary deflection in the second coil. We have observed that a potential difference is induced in the secondary coil whenever the electric current through the primary coil is changing. So, we can conclude that the process by which a changing magnetic field in a conductor induces the current in another conductor is called electromagnetic induction.
Download Spark Learning app. Hello. Oh. Oh.
Huh? you.